I'm Mary, your lab partner. Today we're going to learn more about transition metals. The IU pack defines a transition metal as an element whose atom has a partially filled d subshell, or which can give rise to cations with an incomplete d subshell. This partially filled d subshell makes them perfect for various uses like catalysis. Catalysts provide an alternative reaction pathway with a lower activation energy, increasing the frequency of effective collisions between the reactants, thereby speeding the reaction up. In this simulation, we will learn more about how transition metals serve as catalysts and the chemistry behind it.
Let's learn more about heterogeneous catalysts. Heterogeneous catalysts are catalysts that are in a different phase from the reacting species. When the substrate comes close to the catalyst, adsorption occurs, where dative bonds are formed between the catalyst and the substrate. Transition metals are suitable catalysts as their partially filled d orbitals facilitate this dative bond formation. After the products form, desorption of products occurs, where the temporary dative bonds are broken in an equilibrium process, as the product concentration is much higher at the surface than the surroundings. However, not all transition metals are suitable catalysts. Suitable catalysts are given by the Sabatier principle. The Sabatier principle is a qualitative method to measure and predict the activity of heterogeneous catalysts. The principle states that for optimal catalysis, the interaction between catalyst and the substrate is just right. The principle can be illustrated with a volcano plot, which plots the rate of reaction of heterogeneous catalysts against adsorption strength. The volcano plot shows that the best heterogeneous catalysts are the transition metals in the middle of the graph, such as platinum. The enthalpy change of reaction is intermediate, as it is a combination of the rate of absorption and desorption. The metal on the graph's left absorbs too slowly, as the substrate-catalyst interactions are too weak, hence requiring higher temperatures. Conversely, the metals on the right desorb too slowly, as the substrate-catalyst interactions are too strong, and desorption is the rate-limiting step. Only the metals in the middle hit the sweet spot between absorption versus desorption strength. Thank you.
Great job! Now let's move over to bench 2 to learn more about homogeneous catalysts.
Now, let's learn more about homogeneous catalysts.
Welcome to homogeneous catalysts. Homogeneous catalysts are catalysts that are in the same phase as the reacting species, which usually exist as ions in solution. Several catalytic mechanisms exist, but in the most common one, the transition metal ion catalyst borrows electrons from the species to be oxidized, and then returns these electrons to the species to be reduced. The key to this lies in the transition metal ion's partially filled d subshell, which enables them to easily gain and lose electrons and change oxidation states. Let's examine the reaction between persulfate ions and iodide ions. Although persulfate ions are very powerful oxidizing agents and iodide ions are easily oxidized by iodine, this reaction is very slow because of repulsion between negatively charged ions. The presence of iron 2 ions offers an alternative reaction pathway that reduces the repulsion between similarly charged ions, significantly lowering the activation energy to speed the reaction up. In the first step of catalysis, the persulfate ions oxidize iron 2 ions to iron 3 ions, while they themselves are reduced to sulfate ions. Next, the iron 3 ions oxidize the iodide ions to iodine, while they themselves are reduced back to iron 2 ions. For a transition metal ion to qualify as a catalyst, its reduction potential has to lie in between that of the two reactants, so that each step's redox potential will be positive. In another mechanism of homogeneous catalysis, the reactants coordinate via sigma and pi interactions to the transition metal ion. The complex acts as a hub to keep the reactants in close proximity with the desired geometries for regiospecific and stereospecific bond breaking and bond forming processes in the migration steps. The bond between the product and the central metal ion breaks, allowing for new reactant species to bond to the metal ion and repeat the catalytic cycle. Thank you.
Great job! Now you've learned more about transition metals and how they use as catalysts. Please do a survey to rate the simulation.